Hello and welcome back. So far we have talked about distributions in general, and today we want to start talking about more specific distributions, specifically about random variables. Okay, so we'll motivate random variables, we'll give some examples, a few definitions, and then we'll show how to visualize them. Right. So first, let's see what matters. So far we talked about things like coins, rolling dice, playing cards, dominoes, marbles, all these things that are lots of fun, but often we do things that are not so fun but still necessary. For example, if you're an internet company, you may wonder how many subscribers you have, or how many clicks you get, or how many viewers have seen your website. Or if you're a manufacturing company, you may wonder about the yield of your product, the weight, of individual items, how many sales you have, and so on. If you're a traveler, you may wonder about how long it will take you to arrive at your destination, or the congestion along the way, or the delay of your ride or of your flight. And if you're a physician, then you may wonder about your patient's age, their temperature, their heart rate, and so on. If you're a student, then you care probably about your GPA, about your tuition, or about the course, the cost of the online course you're taking, or the length of the assignments that you get. And everyone cares about their income and about cost of things. So what do all these things have in common? They all have to do with numbers. And so numbers are very important, and specifically random variables whose values or numbers are important to us. And a random variable is, in fact, a random outcome whose value is a number. Okay, so what we're going to do now is going to start studying random variables. Those are random outcomes whose values are numbers. All right, so let's see how numbers are different from outcomes like those we have studied so far, like coins and heads and tails and so on. So first of all, the distribution, P of x, we have a few more features. So because it's a number, we can view it on a line. For example, we can say that the probability of 1 is 0.2, the probability of 3 is 0.5, probability of 7 is 0.3, and so on. So we can view the values of x on the real line because they're numbers. Okay. We can also express them as a function. For example, we can say that the probability of x is 1 over x squared. It would have been more difficult if we looked at the probability of heads and the probability of tails, or the probability of different kinds of breads and so on. We cannot write it as a function of the of what type of bread or type of vegetable we're looking at, right? And we can also consider properties of these distributions. For example, we can say they're decreasing if the distribution looks like that, or if it's concentrated, if it's distributed over a narrow interval, and so on. Also, for the random variable itself, x, there are some extra features that we can look at. For example, we can perform operations. We can look, if we're at x, we can look at x plus 1 or x squared, something we could not do with heads or tails. We cannot say heads times tails, and so on. We can also combine variables. We can look at, we have random variable x and a random variable y. Maybe that's your salary and your spouse's salary, and we can add them up, add those two random variables. We can consider certain properties. For example, we can look at what is the average value of x, and so on. Again, things that we could not do when the outcomes were just some arbitrary values, not numbers. All right. So we distinguish between two types of random variables, and they're based on the size of the sample space omega. Okay. So one is when omega is finite. For example, 1 to 3. The e or pi, so here we have 3 values, 2 values, or countably infinite, for example, distribution over the natural numbers, and distribution over the integers, over the positive numbers. And all these random variables are called discrete, those that are either finite or countably infinite. Okay. The other type are distributions that are where the sample space is uncountably infinite, and for example the intervals from 0 to 2 or -1, 3, union 4, 5, the union of those intervals, or the real line, and so on. And those are called continuous random variables. So we have these two types of discrete and continuous random variables. And of course, there's also a mixture of the two. So you can get something which is distributed over the interval from 0 to 2, or e, or pi. Okay, so these are called mixed random variables. Okay, so we have these two types and then some combination of them. Okay, and discrete random variables are a lot closer to what we have done before, so we're going to start with them. Okay, so as we said, we've seen things like that. For example, we've seen several examples that had number outcomes. For example, we rolled a die and the number was 1 up to 6, so it was an integer. Or we looked at the number of heads in 3 coin tosses. So the number of heads was a number between 0 and 3, an integer between 0 and 3. Or we look at the values of a domino tile, was an integer between 0 and 6, and so on. But we did not use the fact that those outcomes were numerical. We did not say, okay, let's look at dominoes and let's add things or multiply things. So if we did them very rudimentary. So we didn't use them very much. And what we're going to do now is going to start using the fact that those are numbers quite extensively. Okay, and we'll start with some familiar examples, then some couple of new examples, and then get to the general formulation. Okay, so first, number of heads, that, as we said, we've seen before. So suppose you toss 3 fair coins. The sample space, the collection of possible outcomes when you toss 3 coins, are tails, 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 heads, and so on, up to heads, heads, heads. Okay, and so the sample space has size, the sample space omega has size 8. There are 8 possible outcomes or triples, and you notice that all of them are equiprobable. All of those, each one of those 8 outcomes has the same probability, and so the probability of each one is 1/8. So if we let x, our random variable, denote the number of heads, which, as you note, is a number, and it's a random number, then we can write the possible values of x here. It's going to be the lowest that x could be is 0, could get 0 heads, and that happens when you have tails, 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 and that has probability 1/8. Or it could be 1, and that happens when you have tails, tails, heads, or tails, heads, tails, and so on. And there are 3 possibilities here. Each one is probability 1/8. So the total probability of observing one head is just 3/8. And the probability of getting 2 heads is the probability we're getting either tail, heads, heads, and so on. That's again 3/8. And the probability of getting 3 heads, that happens only if all coins turn up heads. And that's just one possibility, and that has probability 1/8. Okay, and you observe that when you sum them up, you'll get 1. Okay, so if you want to draw them on a line, you can write here 0, 1, 2, and 3, and the probabilities are going to be 1/8, 3/8, 3/8, and 1/8. And we can see we can draw this probability like that on the real line and write the probabilities here. Right. Now, if you want to specify the random variable, we have a few ways to do it. So we have the ways that we have seen before. So, for example, we can do it explicitly. We can say, as we've done for the tetrahedral die, you can say that the probability of 1 is 0.1, the probability of 2 is 0.2, 0.3, and 0.4. So we did it explicitly. We can write it as a table. So we write here x and px like that. Okay, but now because we're looking at probabilities of numbers, we have a couple of other ways of doing it. We can write it as a function. For example, here the probability, we can specify this probability as the probability of x is x over 10. So for example, the probability of 2 is 2 over 10, which is 0.2. The probability of 4 is 4 over 10, which is 0.4. Okay, so we can specify them as a function, and we say it's all for all x between 1 and 4. And we can also draw it as a graph. Okay, and there are a couple of ways to do that. We'll show 3. First, you can show us a histogram. So here is x and px. So this says the probability of 1 is, let's say, 0.1, which would need to write. Probability of 2 is 0.2. The probability of 3 would need to write here 0.3. Probability of 4 is 0.4. Okay, so that's one way. Or we can draw what's called the stem plot. looks like this. The probability of 0 is 0.1, the probability of 1 is 0.2, probability of 3 is 0.3, and probability of 4 is 0.4. Or we can draw what's called a plot, which is where we just connect these values, the probabilities. So it will look like this. So we have here 0 connected to 1, to 2, and to 3. Here it's a straight line. Okay, and so we can do all those, and we can do them because we could write the value of our outcome, which was a number, on the real line like this. Okay, right. So these are different ways of specifying the distribution of a random variable. Right. Now, as before, we have a probability mass function, which is what we described until now, so we call it PMF, as we recall. And what it is, it's a mapping P that maps the sample space to the real numbers in such a way that each value is non-negative and they sum to 1. Okay, and so to specify the PMF, we need to specify omega, the sample space, and P. Okay, now omega for random variables is going to be a subset of R, because the random variables get a number value, so it's a subset of the real numbers. If the random variable is discrete as opposed to continuous, then this subset of the omega is going to be a subset of the real number, and the subset is going to be finite or countably infinite. Okay, and P, as we said, has to be non-negative. P of x is non-negative for all x in omega, and if you sum over all omega, the probability of all elements in the sample space, that should give you 1. Right. So again, for a random variable, as before, we have the probability mass function, PMF, or the distribution, except that now it's a subset of the real numbers, and then P of x, this is as we had before. Right. Okay, so as always, so many people work on probability. Different people use different notation, and just want to mention a few variations. So for discrete distributions, this omega is always is going to be a subset of R, and often for discrete distribution is going to be the set of integers, or the set of natural numbers, or the set of positive numbers, or subset of these sets. For example, 1 up to n. And P of x, the probability of x, sometimes we write as P sub x. It's just fewer parentheses to write, maybe a slightly cleaner notation. And because x is often distributed over the integers, then sometimes instead of P of x, we just write P of I. Okay, P sub I. And then what we would have is that Pi is bigger than or equal to 0, and summation Pi is 1. All right. Now, if even discrete distributions are further can be further classified. There are two types. A discrete distribution could be, as we said, finite, and that's when the size of the sample space omega is some number n in P, a set of positive numbers. So it's not infinite; it's some finite number. Or it could be infinite, and that's when the size of the sample space is infinite. And then necessarily it's what we called aleph naught, meaning it's countable. Right? Let's look at finite distributions. So here, as we said, the size of the sample space is n, which is a finite number. So in order to specify distribution, we need to specify just the probability mass function, the distribution itself. And so we can just say what is P1, P2, up to Pn, if, for example, its distribution is distributed over 1 up to n. And necessarily for all I between 1 up to n, Pi, each of those has to be non-negative, and summation Pi, I going from 1 up to n, is equal to 1. Okay. And we have a couple of types of finite distributions. They could be, for example, uniform. That's when all the Pi's are equal, and in that case, it's going to be equal to 1 over n, and this can be shown like that. So we have here all the values, and each of them have the same value, so the same height. So it's uniform if all the heights are the same. Or it could be increasing, and that's when P1 is less than or equal to P2, and so on up to Pn. And then it will look like that. So the values are increasing. Or it could be decreasing, where P1 is bigger than or equal to P2 and so on up to Pn, and it's going to look like that. And notice that when we say increasing or decreasing, we allow for things to be the same. So there could be actually a couple of values here that are the same, but in general it goes down or equal, but will never go up if the distribution is decreasing. All right. Now, for infinite distributions, the size of the sample space is infinity. And you can have one-sided infinite distribution, and that's when you have P1, P2, P3, and so on that goes to infinity. And notice that infinite distribution cannot be uniform, and that's because if P is equal to 0, if it's uniform, then all of them are going to be equal to some value P. And if this value P is 0, then the sum is going to be 0, and we need that the sum of the probabilities has to be 1, so that's not going to work. And if P is bigger than 0, if you have a uniform distribution over infinitely many elements, and if each of them, because it's uniform, all of them have the same value, which we're calling P, if this P is now positive, then the summation is going to be infinite, because you have infinite times some positive number, and some is going to be infinite. Again, it's not going to be equal to 1. So you cannot have a uniform distribution over infinitely many zeros. Infinitely many values. You can have a uniform distribution over a finite number of values, but not over an infinite number of values. All right. Also, the distribution cannot be increasing, and that's because if for some I, Pi is going to be positive, let's say P5 is positive, then from that point on, Pi plus 1, Pi plus 2 are all going to be positive, in fact, all going to be bigger than this Pi. And because they're all larger than this Pi, then the sum is going to again be infinite. Okay, so again, infinite distribution cannot be uniform, and they cannot increase. Okay, on the other hand, they can decrease. For example, you can have a distribution such that P1 is 1/2, P2 is 1/4, P3 is 1/8, and so on. And to see that, observe, so it's the distribution is shown like this. It's decreasing and starts at 1, 2, and will keep going down. And to see that, notice that if you add those probabilities, for example, if you just take 1/2, that's going to be 1 minus 1/2. If you take the sum of the first two, 1/2 and 1/4, that's 3/4. That's 1 minus 1/4. If you take the sum of the first three, 1/2 plus 1/4 plus 1/8, that's going to give you 1/2 and then 3/4 and then 7/8. So that's 1 minus 1/8. So if you take the sum from 1 up to n of 1 over 2 to the I, that sum is going to be equal to 1 minus 1 over 2 to the n. Okay, so like we said here, if you take 1/2 plus 1/4 plus 1/8, it's 7/8, which is 1 minus 1/8. And that's true in general. So if you take the sum of all the elements up to infinity, that's going to be 1. And that's why this probability is summed to 1. So you can have infinite distributions that are decreasing, like that one. Okay, and you can also have double-sided infinite distributions, and that's distribution where you have P1, P2, and so on to infinity, and possibly P0, P minus 1, P minus 2, again going to minus infinity. And as one example, you can take this distribution, 1/2, 1/4, 1/8. You can divide it into 2, so you get 1/4, 1/8, and so on the right side. And then you can have 1/4, 1/8, and so on the left side. The right side will sum to 1/2 because it's this distribution over 2. The left side will sum to 1/2, again because it's the same 1/2 of this distribution. And together they'll sum to 1. And if you draw it like this, it will start here and then go to infinity on the other side. Okay, so just to summarize, you can have infinite distributions, but they cannot be uniform. They cannot increase, but they can decrease, and they can decrease on one side or decrease on both sides. All right. So now, just a little formally, if one wanted to have a formal definition of a random variable, then people would say that it's a function, it's a mapping from the sample space to the real numbers. But in this course, we're trying to simplify the terminology and just focus on the math or the intuition. And so we don't need to worry. We can just pretend that the sample space is what you start with, which is maybe the real numbers. So we can just say that for us, a random variable is going to be a number-valued random experiment. And we don't need to worry about the formal definition. Okay. All right. So to summarize, we talked about random variables. We described the motivations, which is that often we are looking at random outcomes whose values are numbers. Okay, and they're useful, first of all, because they arise in real life, and also we can operate on them, which makes them even more useful, like we can add random variables and so on. We gave a couple of examples, and then we defined what the PMF, the probability mass function for random variable is. We saw how to visualize them using histogram, using plots, and using stem plots. And next time, we're going to talk about cumulative distribution functions. See you then.